Hey, this is Dr. Riley, and in this module we are going to focus on the definition of the atom. Atoms comprise our bodies, the air we breathe, and the physical objects that we interact with every day. So understanding the modern model of the atom, as well as the historically relevant simplified models of the atom, enables us to understand and predict the outcomes of the chemical reactions that are driving our ability to breathe or are creating the materials we handle. It's really important to understand what an atom is. Atoms are incredibly complex in their definition, and so when I don't understand something like that very well, I begin by Googling it, which is what I did today. Some of the top hits for the images I found of the atom are shown here. All three of these are gross oversimplifications of what an atom actually is. By the end of this module, you should be able to explain a little bit about what they got right and what they got wrong in each of these three diagrams. In chemistry, we often use simplified or generalized models to help us grasp basic principles before we move on to more abstract ideas that are hard to conceptualize or draw in two-dimensional pictures. But to truly get chemistry, you have to wrap your head around the definition of an atom, the existence of which was formally proposed in at least the 5th century BC. Most chemistry textbooks will walk through piles of experimental evidence that eventually gave way to what we call our modern definition of the atom. Particularly notable among the historical perspectives on the atom were those from the English scientist John Dalton, who proposed these three hypotheses that together make up Dalton's atomic theory. He said that elements are comprised of extremely small particles called atoms, that atoms of a given element are identical, they have the same size, mass, and chemical properties, and that atoms of one element are fundamentally different from those of another element. He said that compounds are comprised of atoms of more than one element, so in any given compound, the same types of atoms are always present in the same relative proportions to one another. Finally, in the course of a chemical reaction, you see a rearrangement of the atoms in chemical compounds. Atoms are not created or destroyed in chemical reactions. So Dalton's framework here is a simple yet detailed enough model to give us an idea of how atoms, elements, compounds, and also chemical reactions are both defined and related to one another. So using Dalton's atomic theory, we can define the atom functionally as the basic unit of an element that can enter into a chemical combination. I've shown an example of this here. This is a simple combination reaction where one type of atom, shown in blue, combines with another type of atom, shown in red, to make a compound, blue-red, in a 1-to-1 proportion. By convention in chemistry, the arrow is used to show the progress of the reaction. So we have the reactants on the left and the product on the right. I've actually shown you two reactions here. So while the top reaction obeys Dalton's atomic theory, the second one does not. The bottom reaction cannot exist according to Dalton's atomic theory. An atom is the basic unit of a given element, so there is no such thing as a half-red atom. And the original definitions of the atom described them as being indivisible, when in truth, they just didn't have the technology to divide them at the time they were being studied. Now we know that you can actually blow apart an atom into smaller subatomic particles. Atoms are most simply subdivided into three main subatomic particles: the proton, the neutron, and the electron. And this leads us to talk about the physical definition of an atom. So physically defined, the atom is a particle with a dense, tiny nucleus in the center. Note that this is not the nucleus of a cell. This is an atomic nucleus. And in this depiction, you can see it as a tiny little purple dot, which is shown as a blow-up to the right. The nucleus is comprised of two types of subatomic particles. It has one or more protons, and we denote those with a P+ symbol, and it includes neutrons, neutral particles. So every proton has a +1 charge, and neutrons are neutral. Protons and neutrons actually have a relatively similar mass to one another, and together they comprise the bulk of the mass of the total atom. because they're surrounded by the third atomic particle, and that's the electrons. Electrons are actually present in a cloud that surrounds the nucleus. Electrons have a much lower mass relative to the protons and neutrons, and they have a -1 charge. I like to write electron as E-. You'll learn complex models eventually in chemistry that describe electrons as existing in probability clouds in three-dimensional space around the nucleus. In this two-dimensional depiction, they've shown this cloud as a fluffy gray area that surrounds the tiny purple nucleus in the center. In a neutral atom, the number of protons and the number of electrons are equal, so the net charge is 0. If you look at the diagram here, you can appreciate the relative size of the very tiny nucleus and the surrounding electron cloud, because this is drawn approximately to scale. So if we go back to our original depictions of the atom, what was good and what was misleading? All three of these depictions show some sort of nucleus that appears to be in the center, and the one in the middle even shows a nucleus that appears to have positively charged subatomic particles and a roughly equivalent number of neutrons, perhaps shown in red. But none of these has the right proportion of the size of the nucleus to the electron cloud. Electron clouds, because they move in probability clouds, are not in fixed orbits, and all three of these show that the electrons are moving around the nucleus in a fixed orbit. So, some good things, some shortcomings of these models. Now, looking back again at our correctly proportioned diagram, I want to draw your attention to the fact that they actually drew 2 neutrons in the nucleus, and 0 is another way to abbreviate that, and 2 protons in the nucleus. Because it's neutral, you can assume that there are also 2 electrons in this system. Turns out I can tell you that this is a diagram of a helium atom. You may wonder how I knew that. This brings us to the point where we need to do a better job of defining what an element is. We classify different types of atoms by the number of protons in a given atom's nucleus. This is also called the atomic number of that element, and that's shown here in red in my diagrams. Elements differ in the number of protons in their nuclei. And remember, because atoms are electrically neutral, an atom has the same number of electrons as it does protons. So what can we do with this information? Well, we find it easy to identify a type of atom using a mass number, an atomic number, and an element symbol, shown together in this format here on the left. First of all, every element is given a formal full name. So my formal name is Cassandra, but some of my friends call me Kay. Just like Cassandra and Kay, atoms have both a full name, chlorine, and an abbreviated form. In the case of chlorine, it's Cl. Big C, little l. Okay? This is a convention. You cannot invent your own abbreviations. And you probably will benefit by learning some of them that you'll use very frequently. Some are 1 letter, some are 2, and some are even 3 letters long. So having an abbreviation such as Cl enables us to very quickly write out a given element or atom when we're writing a chemical reaction or a molecule. The second bit of information shown here is the atomic number, right here at the bottom. Again, the atomic number is simply the number of protons in that given element. So for chlorine, there are 17 protons in chlorine. That's part of the definition of what chlorine is. Every element is going to be identified by an atomic number. It's only ever the number of protons. So it's very important to know that that means nothing more and nothing less than the number of protons in a given element. So if there are 17 protons in chlorine, and this is electrically neutral, we know there are 17 electrons. The last part of the puzzle is to understand the mass number. The mass number is simply the number of protons plus the number of neutrons. In this case, that number is 35, for example. So if you need to figure out the number of neutrons, which is the one thing we're missing to answer this question here, you need to take the mass number, 35, which is P plus N, and subtract the number of protons, which is 17 coming from the atomic number, and that should give you, by simple math, the number of neutrons. In this case, it's 18 neutrons. Except for one form of hydrogen, all atomic nuclei contain both protons and neutrons. I want to practice this new skill one more time because we can use a shorthand convention to extract information about an atom that you need to know. So if you're asked to determine the number of protons, neutrons, and electrons in this atom of hydrogen, where would you start? I begin at the subscript, the atomic number, 1. You should remember the atomic number is equivalent to the number of protons and the number of electrons. Okay, so that is 1 in each of these cases for this hydrogen. How many neutrons? Well, since the mass is the sum of the protons and the neutrons, you need to take the mass number, which is shown here at the top, subtract the number of protons from the bottom, and that will give you the number of neutrons. So this particular type of hydrogen has 1 proton, 1 electron, and 1 neutron. And we know it's hydrogen because it has 1 proton. That's the definition of that element.